today we'll see how to determine the common mode gain of the differential amplifier and what is the significance of this common mode gain. So can you see this screen here?
Yes, sir.
Okay. So common mode voltage, common mode gain, common mode rejection ratio. So first we'll try to define these different parameters and then we'll see how to determine those. So let's say this is our differential amplifier. The symbol is same for op-amp. Op-amp is also an amplifier with two inputs, and so is differential amplifier. So this is a triangle is the symbol for the amplifier in general, and differential amplifier has two inputs, same as the op-amp. The only difference, we take positive at V1 and negative at this V2. So that is the only difference here. But op-amp we take positive at V2, right? Negative at V1. So this is our voltage, the differential input voltage VID, right? Plus and minus. So VID is our V1 minus V2. So now okay. So that's the differential voltage, and differential gain we define as the output divided by differential input. That was our differential gain. Now, what is the common mode voltage? Common mode voltage is when you take the average of these two. So VCM is the average of these two. When you take the average voltage, so that is our common mode voltage, and the gain to that, due to that, call it common mode gain. So common mode gain denoted by ACM will be V naught by VCM. So common mode voltage will be the voltage that is being applied to both the input terminals, and that we can show like this. So that is our common mode voltage, V0. This is here you have plus terminal and negative terminal, right? So there's differential amplifier with common and the differential input, differential amplifier with common mode input. But in general, if you consider this one, this first circuit, differential amplifier has actually both the inputs at the same time. You have the common mode voltage and also the differential voltage at the same time. And how is that? Because and you see that V0, V1, okay, V1 we can express like this. Since V1 we are taking positive, V2 negative, that means V1 is at a higher voltage than V2. That is how we are assuming here. So then this can be written as VCM plus VID by 2. And V2 we can express as VCM minus VID by 2. And these two we can easily derive, right? One is this equation. The definition of differential input voltage VID is V1 minus V2. The other is the definition of the common mode voltage, that is VCM is average of these two. Right? If you combine these two, we get these two. Right? And you see, from this you can easily get back to this. You take V1 minus V2, and V1 minus V2 will give you VID, because it's half VID minus VID. And if you add them up, these two will cancel out, and you get this one. Right? So this is nothing but derived from these two expressions. Right? For example, if we take, let's say our V1 voltage is, what do we take? VCM, let's say V1 is 12 volt and V2 is 10 volt, right? So if we have the inputs like this we can easily express as V1 as 11 plus 1, and this you can express as 11 minus 1, right? So you see what we have, this 11 here is the common in both the inputs, right? This is our common voltage that we have at both the inputs, and that we define as VCM, the common mode voltage. The other is this part, which is the difference, right, between this, and it's half of VI, right? So, oh, sorry, this should be minus. So that is minus. Okay. So easily see that we have expressed the V1 and V2 in this form, VCM plus VID by 2 and VCM minus VID by 2. So if that is our V1 and V2, so here in this case VCM will be 11 volt and VID will be 2 volt. So what do we have? That it shows that for differential amplifier, we actually have both the common mode and the differential voltage at the same time. Right? We have both the voltages. And so that we can show like this, that yeah, maybe one space may not be enough, so we take a fresh space. What happened? We are at the end of the. Okay, so that was the problem. Okay. So we put it on top. Okay. Okay, so the expressions that we have got now for V1 and V2. So we have got V1 is VCM plus VID by 2. And we have V2, which is VCM minus VID by 2. And that we can show in circuit like this. We have both the input voltages at the same time. So we have the common mode voltage called VCM. And then for so we branching out, we have two input terminals, one for V1 and V2. So V1 will be higher. So we have this, right, a plus, and this will be plus and minus like this. And we have VCM here, and this will be half VID. So that will be VID by 2. And this will be also half VID by 2. And this is our V1. So V1 is VCM plus VID by 2. And this will be our V2, which is VCM minus VID by 2. So V1 is greater than VCM by this voltage, VID by 2. V2 is less than this voltage by half VID. This is how we get the V1 and V2. And then that will be connected to the input of the differential pair. So that we show like this, goes to the input of the differential amplifier. And so that is our V0. Guys, any question?
No, sir.
Okay. So that is our differential voltage here. The difference between V1 and V2, that's a VID. And also we have the common mode voltage going into both the input terminals. So then the output will be a combination of both the input and both the common mode and the differential voltage. So V0, previously we are writing for the differential amplifier, the differential gain times the differential input voltage. But now we recognize that along with this differential input voltage, we also have the common mode input voltage, and that also will have some contribution to the output voltage, and that we can write is plus the common mode gain that we have already defined for the common mode voltage times the common mode voltage. So we have the contribution coming from the differential input voltage, and also we have the contribution coming from the common mode voltage. So that will be our total output, right, from the differential pair. Now, differential amplifier, they are designed specifically to amplify the differential voltage, the difference between the two input voltages. That is what they are supposed to do, right? So, but in the output, as we have discussed here, that we not only get the output due to the differential input voltage, we also have another component in the output voltage that is due to the common mode voltage, and that is our undesirable part, right? That's not a desirable part, right? That is what we do not want. We want only the differential output voltage, not this part. So for the ideal differential amplifier, if the differential amplifier is ideal, in that case the ideal differential amplifier should amplify only the differential voltage. It should not amplify the common mode voltage, right? So for ideal differential amplifier, the common mode voltage ACM should be 0, right? For ideal differential amplifier. There's the ideal situation, but for practical differential amplifier, will not have this 0 because there are so many parameters, so many different factors, non-ideal factors that will affect the output and have some contribution due to the common mode input voltage. Now, how do we quantify that effect of the common mode voltage in the output voltage? So that is taken into account, and that is measured by another parameter that is called the common mode rejection ratio. So now we'll define what is common mode rejection ratio. We can express this, the output voltage like this. We have ACM divided by EID times ECM by EID. So this is how we can express this output, and that is the VCM by EID. Now, this denominator, what we have, AT by ACM, the ratio of differential gain to the common mode gain is called the common mode rejection ratio. And in short, it is written like this: CMRR. CMRR stands for common mode rejection ratio. As you have seen, that ideal differential amplifier, the common mode gain should be 0. So this part should be 0. So then if this is 0, then this becomes infinite for ideal differential amplifier. So for ideal differential amplifier, the common mode rejection ratio should be infinite because common mode gain is zero. And what does this CMRR indicates? It is in the name of this parameter, common mode rejection ratio. Rejection, that means that how effective the differential amplifier is in rejecting the common mode voltage, right? The higher is the CMRR, that means the more effective is the differential amplifier in rejecting the common mode voltage. Right? So for practical amplifier, practical differential amplifier, because ideal is infinite, but practical differential amplifier will always have some non-zero value, right? ACM will be not zero, right? For practical differential amplifier, right? And CMRR will be finite, right? It will not be infinite, right? You will have some finite value for CMRR. But ideal is zero, infinite. Infinite means this becomes zero. And then if this becomes zero, the output becomes ADVID, right? So that is the ideal situation. Ideal situation, the differential amplifier is 100% effective in rejecting in the common mode part, right? The common mode voltage. And you get the output due to only the differential input. But for practical, it's not 100% effective in rejecting the common mode voltage, and output you get due to the both the differential input. You have this one for differential input, and you have the output due to the common mode. Output due to the common mode input voltage. So you get to see that this factor here 1 over CMRR. So for practical amplifier, the higher is the CMRR, the more effective the differential amplifier will be in rejecting the common mode voltage. The higher is this parameter, the lower will be this part, right? The lower will get this part, and the output will be dominated by the differential output voltage. So for practical, we want CMRR, CMRR to be as high as possible, right? The higher, the better, right? The higher is the value of CMRR, the better, the more effective the differential amplifier will be as a differential amplifier, right? Is that clear, guys?
Yes, sir.
Okay. So that's an important concept to understand. That is for practical differential amplifier. So this is another measure of performance of the differential amplifier. The common amplifier, or conventional amplifier with one single input. We have the gain, the input resistance, right? The bandwidth. These are the parameters. And differential amplifier will also have those performance parameters, the same that we have for the single input amplifier. And along with those, we have other performance parameter for the differential amplifier, that is common mode rejection ratio, and that is an important performance parameter for the differential amplifier. Because if CMRR is low, then the output will have the contribution from both the differential input and the common mode input voltages. And why it is so important, CMRR? Because you see that usually the common mode voltage is much higher than the differential voltage, right? Usually the common mode voltage will be in the range of volt, right? Whilst the differential voltage usually in the range of millivolt, or sometimes can be smaller. So why the common mode voltage is high? Because it is due to the bias voltages, the voltage that we apply to the transistor to bias the transistor, right? The DC voltage. So usually the common mode voltage is high in the range of volt, while the VID will be very small in the range of millivolts. So almost they are 1,000 times greater, right? So unless the CMRR is very high, right, this contribution will be significant because the large magnitude of the common mode voltage. So it is important for a parameter for the differential amplifier, the common mode rejection ratio, and also it is important that the differential amplifier has quite high value for the common mode rejection ratio. And how high is a good value, right, for the differential amplifier? Usually in the range of 10 to the power 5 to 10 to the power 6, right? If CMRR is in this range, then the differential amplifier is considered to be a good differential amplifier. Right? Otherwise, the performance will, will not be the optimum performance or not a good differential amplifier, because output will have significant component coming from the common mode voltages. So now that we have discussed the parameters, the common mode voltage, common mode gain, the common mode rejection ratio, so now we'll discuss how to what is the common mode gain for the differential amplifier. Yeah, how do we determine the common mode gain? So here we have a differential amplifier where we have a common mode voltage, the same voltage applied to both the input terminals. So it has only common mode voltage, doesn't have any differential voltage, and the output VC1, VC2, or VOD, any of these outputs will be due to only the common mode voltage VCM, because there is no differential input voltage. So we can analyze this circuit, and we can try to determine the common mode input, the common mode gain. Right? The output will be common mode voltage times the common mode input voltage. Right? And V0 can be we can take from the collector 1, or we can take from collector 2, or we can take differentially, right? And we'll see that we'll have different gain expressions for the different outputs, like also similar to that what we have got for the differential voltage. So first, what we do, we set this DC bus voltage and current to 0. Right? Now, here we have to consider one one thing here, that is when you set this 0, this gets short circuit, this gets connected to 0, because ideal the voltage source will have 0 resistance, and this will get open circuit here, right? Because ideal the ideal current source has infinite output resistance, and then that is that becomes open circuit. But here, so usually the current source is shown for the output resistance for the current source is shown like this. So let's say these are output resistance denoted by RE for the current source. This is shown to be connected in parallel, right? And this is infinite. This resistance is infinite for ideal current source. Ideal current source, this resistance is infinite, and when you set this current to 0, this becomes completely open circuit. Now, if this becomes completely open circuit, since you are applying the same voltage at both the input terminals, what happens? There will be no current flowing. Right? The I will be 0. The emitter current will be 0, because you have if you say think about the small signal, the model, we have here RE and RE, we have here VCM, and also at this end also you have VCM, right? At both the end you have same voltage, so there will be no current flow. Current will be 0. And if this emitter current is 0, so this collector current here, right, both the currents will be also 0. And if both the currents are 0, then also all the voltages will be also 0. Right? So that means there is no output voltage due to this common mode voltages. But that is not the situation in real differential amplifiers, because real differential amplifier will not have infinite output resistance for the current source. Right? This is ideal situation. Real differential amplifier will always have some finite output resistance for the current source, and so we do need to consider that factor, right, when you try to determine the output resistance, or determine the gain for the common mode input voltage for the differential pair. So now we include this RE, because this is our amplifier is not a practical, not an ideal amplifier. It is a practical amplifier. So when we include that, now when you set this current to 0, so this part will become open circuit, right? This part will become open circuit. But what happens here? we have this this part, the current source becomes open circuit, but you will have this connected, this RE, that part goes to emitter, and this part will get shorted to ground, right? So that is how now we'll have, if you consider the current source to be a practical current source, not an ideal current source, for the differential, when we are trying to determine the gain for the differential amplifier, we did not consider this RE. We assume this is infinite. But even if you consider for differential gain and this RE will not have any effect, right? This RE will not have any effect, because why it will not have any effect? Because the current will flow like this. It will not go like this, right? For differential input voltage, this will flow like this. Will not, so RE will not have, doesn't matter, I mean, how low or high value we have here, it will not have any effect because current will flow like this. But for common mode voltage, current cannot flow like this, right? This way current will be zero. But if you have this connected to ground, right? So now this current cannot be zero, right? Because the current will now flow like this, right? So we'll have current flowing in both the emitters, and that will going to the ground. You can have resistance here, low resistance, high resistance, or zero resistance, even RE if it is zero. But current source, they have high output resistance, it cannot be low or zero. It will have some value. But even if it is low, I mean, or high, it doesn't matter. The current will flow. Right? And this is how the current will flow. So what do we get now that, so now this current is not zero. That's the problem. So now this current will not zero. This current will flow because it is connected to ground. Here we have current, right? IB, the base current flowing at both the input terminals. And here we have emitter current, right? IE. And this current, they will flow in this direction. They will flow down, right? From this part and from this part. Right? They will flow down. And this RE, we can show it like this. Connected like this. Any question, guys? So now you have current flowing here. It will not be zero.
Sir, why is this RE, small RE? Why not R5?
we're looking from the emitter side. Okay. We're looking from the emitter side. Sorry, if we're looking from here, right? Because this part is connected to ground. The current here is flowing IE, right? And so the resistance is looking from here is small I. Right? Is that clear?
Yes, sir.
So here you have current alpha I, and also here alpha I. So the difference here, if you had the differential input voltage, the current here flows down, current here flows up, because in that case the current flows like this, right? From Q1 to Q2. But in this case, both the currents are flowing in the same direction, and they're flowing into the ground. So here, in both the collectors, the current is flowing down. So that is the difference with the differential input voltage. You have the currents flowing in the same direction, right? So then you will have VC1 and VC2, right? You have both the input and voltage at both the collector terminals, right? And then we can write that the VC1 is minus alpha IE RC, and VC2 will be also minus alpha IE RC, and VOD will be the VC2 minus VC1. You see that since these two transistors are identical and we have the same resistance RE, so these two currents will be, I mean, they will have the same magnitude, same kind of be flowing. And so the VC1 will be and VC2, these two are same, and they are same magnitude, and that will be 0. And so it is clear that the common mode voltage, when you take the output differentially, that is 0, right? So gain, your ACM, when you take the output differentially, so the common mode gain is 0. So that is true for differential output. Right? The common mode gain due to differential output voltage is 0. But again, see, this is an ideal situation, right? Ideal situation. Why ideal? Because we are assuming that these two transistors are identical, everything are identical, these two resistances are identical, exactly same value. But in real life, you don't get anything identical. No matter how much you try, there will always some difference, no matter how small is the difference. So if you take two 10K resistors, you'll see that there is some difference between those two 10K resistors. One is little high, one is maybe, it can be 1% or 0.1% or 0.01%. No matter how small, there will be some difference, and that difference will lead to some voltage difference between VC1 and VC2, and that will lead to some, non-zero output voltage VOD, and that will lead to some non-zero gain for the differential amplifier. So for practical amplifier, the common mode gain will not be 0 even if you have this differential. If you take the output differential, it will have some non-zero gain. And of course, if you take output from a single node, you will always have some voltage, and there will be some gain associated with that. So now we'll try to determine what will be the common mode gain for VC1, VC2. Now, how do we determine that? For that, we need to determine the current I, right? What is current I? If you can determine current I, then we can determine the gain. Now, if you look at the circuit, you see that this RE, one single resistor, we can split it into two resistors and show it like this. If we split into two separate resistors, we can show like this. So RE split into two resistors. So combination of these two should be RE. So now each of these should be 2 RE. So you take the parallel combination. The parallel combination will be your just RE. So we remove this. So now we have in the RE split into two equal parallel resistors. Okay. So now this current IE will flow straight down, right? So you have IE flowing here, also IE. It's not flowing this way because you have equal resistors and voltage at these two ends will be same. So this current will be divided equally between these two resistors. Now look at this circuit here. The input VCM we can show like this instead of here. So we have VCM here, common mode voltage, another VCM at this end, common mode voltage, right? And see, this current is going straight down, right, through the resistor to RE. So this current is not flowing this path, right? So this has no effect on the circuit. Even if we remove this, everything remains same, right? This current is flowing right down. And now if we remove that connection here, so that has no effect. So it looks like two separate independent circuits, right? Two separate independent circuits. Now each of these circuits, they are called the common mode half circuit. Like differential half circuit, these are called the common mode half circuit. We have the common voltage VCM applied to both the input terminals, and in the emitter we have this resistance, the output resistance of the current source, twice of that 2 RE, and this is high resistance. Any question, guys? No question. So now see that if these circuits, they are the common emitter amplifier configuration with a resistance in the emitter, right? Common amplifier with emitter resistance. So we can easily determine the gain of these circuits. So what will be the gain? This is for say VC1 by VCM.
So minus GM parallel GM into R not parallel RC.
No. Common emitter amplifier with emitter resistance.
Oh, sorry, sir. I didn't see the emitter resistance. Sir, then resistance on the collector divided by resistance on the emitter.
Right. The common emitter amplifier with resistance in the emitter, we can write the gain as the ratio of the two resistances on the resistance in the collector divided by resistance in the emitter. So that is the simple formula. you can apply to write the gain expression, but you have a minus sign. Common emitter has a negative gain. So resistance in the collector is just RC. So just write RC, and then the resistance in the emitter, which will be small RE plus 2 this RE. Now that will be same for the other one, just VC2 by VCM. That will also have the same gain expression, because everything is same for the two circuits. So gain, the common mode gain for both the outputs from the collector terminals are same, right? That is RC divided by RE. Now here you see that RE will be much smaller, because the RE is the output resistance of the current source, and that we know high, it will be in the range of hundreds of kilo ohms, and so that will be much larger than a small RE, which is in the range of few ohms. So that will be much larger. So we can always approximate this expression to minus RC divided by 2R. Is that clear, guys?
Yes, sir.
Okay. So we have determined the common mode gain for the differential amplifier, that for single-ended output VC1 by VCM, and which is same as also VC2 by VCM. They have the same gain, and which is minus RC divided by 2RE. Right. And that is the common mode gain for common mode gain for single-ended output. When the other one is VOD by VCM, common mode gain for differential output, and that is 0, assuming everything is identical, and which we call the ideal case, right? So we'll not go into the non-ideal case now. Even for non-ideal case, this will be small, because there will be small difference between the two sides. So we'll have some output voltage, but even that will be small compared to what we have for the single-ended output. There's nothing cancelling out, so usually it is large, right? So now the common mode rejection ratio. What will be the common mode rejection ratio for this differential pair? And that is defined as usually we take the absolute magnitude is taken here. What happened? Something usually we take not the sign, but we consider the magnitude of this ratio. That's defined as the ratio of the differential gain to the common mode gain. So that is how we define the common mode rejection ratio. Now the common mode gain is 0 for the differential output. So that will be infinite. That will be infinite, since ACM is 0 for differential output. So for differential output, we get the infinite common mode rejection ratio, if we are considering this an ideal differential amplifier, ideal situation. But for single-ended output, it will not be 0. Single-ended output, so we have common mode gain, which is minus RC divided by 2RE. Then we have to put AD, right? Differential gain. What is the differential gain for the single-ended output? Okay. Do you remember? The AD, a differential gain, is minus half GMRC if you are taking output from collector BC1, or if you are taking from collector BC2, it is half GM plus half GMRC for BC2. So now it doesn't matter here, minus plus doesn't matter, because anyway that will be, we'll be taking the absolute magnitude, so that will cancel out. So that is how we can express this. Now taking the absolute, the RC and RC here will cancel out, right? So, and we have these two will cancel out. So what will be left with? Will be left with GM RD. So that will be the common mode rejection ratio for, sorry, that's not differential. That is the CMRR for single-ended output. Any question, guys?
No, sir.
So differential amplifier will work as a better differential amplifier when you take the output differentially, because it's cancelling out the common mode voltage, right? And you get even for non-ideal case, if you don't use this small. For ideal case, it is exactly zero, but even for non-ideal, it is small. And so the gain ACM will be small and common mode rejection will be high. But for if you take this thing output from single node, then it doesn't cancel out, and the CMRR will be low, right? And it will not that effective as a differential here. So now to have an idea about the magnitude, level of magnitude we can have, if you take some, if you take a numerical example here. So let's say our collector current IC is 1 milliampere. Then GM will be your IC by VT, and that will be about, we have done this before, about 40 milliampere per volt. And RE, if we assume a value, let's say about 100K. Right. So if that is the value of RE, then you see that your CMRR here you have 40 times 100, that will be about 4,000. So that will be your CMRR for single node output. That's not that high. We said about the CMRR is about 10^5 or 10^6. So there's a good performance level for the differential pair. Here is only 4,000. Yeah. So to have a better differential pair, so this RE should be high, the output resistance. It is, if it is if you have in mega ohms range, we have 100 kilo ohms. If you have it in, let's say 10 mega ohm, then 100 times greater than 10 to the power 5. So that is how we can improve the performance of the differential amplifier. Any question, guys? No question?
No, sir.
So, okay, guys, we'll stop here today because we don't have much time, and so we don't want to go into the next topic, and that will start in our next class. So we have discussed about the different aspects of the differential amplifier, different performance parameters, how to analyze, right? And the next class we'll see multi-stage differential amplifier, like we had for single stage. We also have multi-stage differential amplifier.